The solar wind hitting Earth right now is traveling at 567 kilometers per second. That is not a speed you can picture easily, so let's make it human. The fastest bullet ever fired by any weapon on Earth moves at approximately 7 kilometers per second. The solar wind arriving at our planet today is moving at 1/3 of that bullet's speed, but what is arriving is not a bullet. It is a river of charged particles so wide it dwarfs the orbit of the moon, streaming continuously from a wound in the sun that has now grown so large it covers more surface area than 60 Earths laid side by side. But that is not even the real story. The speed matters. The size matters. But neither of those numbers is the thing that has space weather physicists watching their monitors with the particular quality of attention that fills a room just before something happens. The real story is what that river of charged plasma does when it arrives. Because what is traveling toward us is not simply fast wind. It is a reconfiguration of the electromagnetic environment surrounding our entire planet. And our planet, in the year 2026, is encased in a shell of technology so intricate, so globally interdependent, so quietly woven into every transaction and navigation and communication we make, that disturbing that electromagnetic envelope is no longer a space weather event. It is a civilization event. And here is where this story becomes genuinely alarming. Because the monitoring is in place, the satellites are watching, the data is flowing in real time, detection is possible. But prediction, real prediction, the kind that would let a power grid operator in Quebec or a satellite controller in Colorado or an aviation authority in London know exactly what is coming and exactly when, prediction is not possible. The instruments tell us a storm is coming. They cannot tell us how hard it will land. Active region 441 has been the sun's dominant story this week. Located near the solar equator, this sunspot region has been the source of B and C-class flares throughout April, with scientists noting it retains the potential for isolated M-class flares at any moment. The kind of flares capable of triggering minor to moderate radio blackouts across the day side of Earth without a moment's warning. But region 4419 is not the primary concern today. The primary concern is the coronal hole that has opened in its neighborhood and is now facing Earth directly. This is a negative polarity coronal hole high-speed stream, a CHHSS in the shorthand of space weather forecasters, and it has been growing, darkening, and aligning with Earth's position since it first rotated into view on the sun's northeast earlier this week. On April 17th and 18th, NOAA's Space Weather Prediction Center issued a G2 moderate geomagnetic storm watch, citing solar wind speeds of 600 to 700 kilometers per second, as likely during the event based on recurrent measurements of the same hole from prior solar rotations. The stream has arrived, and the aurora it has already triggered has been seen across the northern United States. Now understand what a coronal hole actually is, because the name makes it sound passive, geological, stable. It is none of those things. A coronal hole is a region on the sun's surface where the magnetic field lines have torn open, not collapsed inward, but reached outward, extending into interplanetary space instead of looping back to the solar surface as they normally do. Where magnetic field lines normally form closed loops that contain the sun's superheated plasma, the coronal hole is a place where those lines are open. They point outward into the solar system like a fire hose with no nozzle. And from that opening, the sun's plasma does not drift outward the way it does in the quiet solar wind. It escapes. It accelerates. It reaches speeds that normal solar wind never achieves. Research published in the Astrophysical Journal in April 2026 by New Mexico State University astronomy graduate student Khagendra Katawal, analyzing 70 coronal holes using data from NASA's Solar Dynamics Observatory, found that approximately 88% of coronal holes show significant magnetic field imbalance, a unipolarity, an overwhelming dominance of one magnetic polarity over the other, and that this imbalance correlates directly with the formation of the fastest, densest solar wind streams. Coronal hole 4419's region is one of those magnetically unbalanced structures. Its field lines are open, the plasma is escaping, and it is escaping toward us. Think about what 567 kilometers per second means in terms of this journey. The sun sits approximately 150 million kilometers from Earth. At 567 km/s, the solar wind from this coronal hole covers that distance in roughly 2 to 3 days. It does not travel through empty space. It plows through the ambient solar wind that already fills the space between the planets, the slower wind moving at 350 to 450 kilometers per second that emanates from the rest of the sun's surface. When the fast wind from the coronal hole overtakes the slow wind ahead of it, they collide. They compress into a region that scientists call a co-rotating interaction region, a CIR. This CIR is not a gentle transition zone. It is a compression front, a pileup of magnetic field and plasma density, and it arrives at Earth before the main high-speed stream. It is the advance shock. The particle density spikes. The interplanetary magnetic field strengthens. And then, embedded in that strengthened field, there's a variable, a single number, that determines whether Earth's magnetic shield opens or holds. That number is the BZ component of the interplanetary magnetic field, and it is the most important number in space weather that most people on Earth have never heard of. BZ is simply whether the sun's magnetic field embedded in the solar wind is pointing north or south. When BAZ points northward, it aligns with Earth's northward magnetic field, and the two push against each other, and our magnetosphere holds. When BAZ points southward, it is anti-parallel to Earth's magnetic field, and the interaction changes entirely. The two fields connect, they merge. The process is called magnetic reconnection, and what it does is open a door in our planet's magnetic shield, a door that the solar wind walks straight through. On April 18, 2026, around 7:41 UTC, conditions escalated to a G2 moderate geomagnetic storm as the BAZ component swung southward and magnetic reconnection began. By 8:25 UTC, the full G2 threshold was crossed. The storm will continue through this weekend. Forecasters are monitoring whether it deepens. And here is where this story connects to something older and far larger than any single storm. Because the question that keeps returning when you sit with this data is not what this storm is doing to Earth. The question is what it reveals about the relationship between the sun and this planet. A relationship that is not static, that has not always been as mild as the last century of electrical civilization would suggest, and that has at least once in recorded history shown its full face. On September 1st, 1859, British astronomer Richard Carrington was in his private observatory at Firs Hill in Redhill, Surrey, conducting routine observations of sunspot activity through darkened glass. Just before noon, he saw something no human being had ever documented before, a sudden, blinding flash of intense white light erupting from a large sunspot group. He watched it for 5 minutes. He noted the time. He moved to get another observer. When he returned, it was already fading. He published what he had seen. And within 6 hours, not days, hours, because a prior CME had already cleared the path of ambient solar wind, allowing this ejection to travel at extraordinary speed. The Earth's magnetic field experienced the largest geomagnetic storm in recorded history. The Carrington Event, as it is now called, peaked on September 2nd, 1859, and it was classified on the modern NOAA scale as the highest possible level, G5. Ice core samples have since determined it was at least twice as large as any other solar storm in the last 500 years. The solar wind speed at its peak has been reconstructed from historical magnetic records at approximately 980 kilometers per second, with a southward magnetic field component between 40 and 60 nanoteslas, numbers that dwarf what is arriving today. What happened next is not speculation. It is documented geology. It is in the historical record. It is in the newspapers of the day. Telegraph systems worldwide failed simultaneously. Operators who touched their equipment reported electric shocks. Telegraph paper caught fire. In Pittsburgh, a telegraph manager described platinum contacts in danger of melting in streams of fire pouring from the circuits. In Boston, people could read newspapers in the street at midnight by the light of the aurora alone. In the Rocky Mountains, gold miners woke before dawn, saw the sky blazing crimson, and began cooking breakfast because they believed the sun had risen. The aurora was visible as far south as the Caribbean, as far south as Cuba, as far south as Panama. A significant portion of the world's 200,000 kilometers of telegraph lines, the entire nervous system of global communication in that era, was rendered inoperable for hours at a time. The economic impact was real. The physical infrastructure of the most advanced communication technology of the time was set on fire by the sky. And in 1859, the total electromagnetic exposure of human civilization consisted essentially of those telegraph wires. What would happen to a civilization that has surrounded itself with satellites, power grids, internet cables, GPS networks, cellular towers, fiber optic switching stations, hospital monitoring equipment, aviation navigation systems, financial trading infrastructure, and nuclear plant control systems? A National Academy of Sciences report placed the answer at between $1 and $2 trillion in damage for a Carrington-class event today, with recovery times of weeks or longer, not hours, because the transformers that would fail are not simple components. They are custom-built, they weigh hundreds of tons, and there are not spare ones sitting in warehouses. This is not a theory. This is documented engineering reality. And we know this because it has already happened at a smaller scale. On March 13th, 1989, a severe geomagnetic storm, described by Dr. David Boatler of Natural Resources Canada as the biggest geomagnetic storm of the space age, struck Earth. At 2:44 in the morning, as most of the province of Quebec slept, the Earth's magnetic field began fluctuating violently. The variations in the magnetic field induced geomagnetically induced currents in the long, high-voltage transmission lines of Hydro-Quebec's power grid. 7 static VAR compensators tripped one after another in a cascade. The voltage on the La Grande network dropped to 0, 2 per unit. All 5 lines to Montreal tripped simultaneously through loss of synchronism. The system-wide blackout resulted in a loss of 19,400 megawatts. The James Bay network went offline in less than 90 seconds. 6 million people lost power simultaneously. It was 2:45 in the morning and the temperature outside was below freezing. The power failure lasted 9 hours. Hospitals ran on emergency generators. People in high-rise apartments had no elevator, no heat, no light. The system restored only because trained engineers worked through the night and into the morning, and because the storm was what it was, a 1-in-50-year event, not a 1-in-500-year Carrington-class event. The solar wind that night carried a peak speed of approximately 980 kilometers per second. Today's stream is arriving at 567 to 700 kilometers per second. Today's storm is G2, not G4. But those numbers exist on a scale that can change, and the direction of change has only one direction. There are 6 million people in Quebec today, roughly the same as in 1989. The grid has been upgraded since then. Hydro-Quebec has installed series compensation, recalibrated protection systems, and established real-time alert protocols specifically because of what happened in March 1989. They believe the modern system could handle a 1-in-100-year event. The March 1989 storm was a 1-in-50-year event. What they have acknowledged, quietly but clearly, is that they cannot guarantee the grid against a 1-in-500-year event. The Carrington Event was a 1-in-500-year event. And according to a probability assessment published in research literature, there is approximately a 12% chance of a G5 level storm per decade during active solar periods. The sun is not dormant. It is awake. And we are just past solar maximum, the peak of solar cycle 25, the part of the 11-year cycle when these events are most frequent and most intense. Consider also who else is exposed. Not just Quebec, not just North America, because coronal hole high-speed streams do not arrive and depart in a moment. They blow continuously for days, sometimes rotating with the sun across multiple passes over weeks, making the source of geomagnetic disturbance a recurring one. The impact is felt across every high-latitude nation where long transmission lines run across geologically resistive rock formations, where induced currents have nowhere to flow except through the infrastructure itself. That means Scandinavia, where Norway and Sweden's power grids run across ancient granite shields. It means Alaska, where the pipeline carrying oil from Prudhoe Bay to Valdez is a steel tube running across 2,300 kilometers of terrain, and where geomagnetically induced currents can accelerate corrosion in that steel at rates that pipeline engineers monitor, specifically during geomagnetic storms. It means the northern tier of the United States, where high-voltage transformers serve tens of millions of people, and where a damaged extra-high-voltage transformer, the kind that cannot be manufactured quickly, that takes 12 to 18 months to build on order, represents not a service interruption but a regional crisis. And then there's the satellite layer. Today, in 2026, low Earth orbit is occupied by thousands of satellites. Navigation, communication, imaging, weather monitoring, military intelligence, broadband internet. During geomagnetic storms, the upper atmosphere heats from joule heating, the same physical process that heats a wire when current runs through it. And that heating causes the atmosphere to expand upward. When the atmosphere expands upward, it reaches satellites in low orbits that normally sit above it, and it creates drag where there was no drag before. That drag slows satellites. When a satellite slows, its orbit decays. When its orbit decays below a threshold, it burns up on re-entry. We have already watched this happen. In May 2024, during the strongest space weather event since October 2003, Starlink lost approximately 40 satellites to increased atmospheric drag during a single geomagnetic storm period. 40 satellites gone, worth hundreds of millions of dollars, because the atmosphere briefly reached up and touched them. The current storm is G2. That level brings intermittent satellite navigation issues, possible GPS corrections needed, HF radio intermittency, and possible surface charging on satellite components. Not catastrophic, but not trivial, and not isolated. Because satellites do not serve themselves. They serve the ships at sea that use GPS to navigate the Strait of Malacca. They serve the aircraft over the North Atlantic that use high-frequency radio to contact air traffic control. They serve the precision agriculture systems across the plains of Pakistan and India and the Midwestern United States that use centimeter-accurate GPS to guide planting equipment. During the May 2024 G5 storm, a loss of satellite navigation precision resulted in a $500 million loss to the U.S. agricultural industry alone, in a single event. The costs of space weather are not future costs. They are ongoing costs. The only question is their magnitude. Now think about the people who actually live inside all of this, not as data points, as neighbors. Think about the 7 million people in New York City, who on a cold March night in 1989 might have lost power the same way Quebec did if their grid had not been luckier. if the induced currents had found a slightly different path, if the granite beneath them had slightly different conductivity. Think about the 32 million people in the greater Tokyo metropolitan area, sitting at one of the highest densities of electronic infrastructure anywhere on Earth, whose grid is not built for geomagnetic events the way high-latitude grids are, whose satellite communication and GPS-dependent logistics make the city function minute by minute. Think about a city like Tromsø, Norway, 77,000 people living at 69 degrees north latitude inside the auroral oval, the precise geographic zone where geomagnetic storms are strongest and where the sky was lighting green and red as this script was being written. The people of Tromsø are accustomed to auroras. They are not accustomed to power failures caused by them. But they live in the place where the electromagnetic door between the solar wind and Earth's surface is thinnest. And they have no more warning than anyone else about when the basis component will swing south and that door will open. There's a thread that connects all of this. The coronal hole, the charged stream, the magnetosphere, the transformers, the satellites, the telegraph fires of 1859, the dark city of Montreal in March 1989, and that thread is one that most space weather discussions acknowledge, but few follow to its end. The sun does not behave in isolation, neither does Earth. The 11-year solar cycle is not a smooth sine wave. It is a complex oscillation shaped by the sun's internal magnetic dynamics, and it interacts with planetary gravitational fields, with the alignment of the gas giants, with the grand solar minimum and maximum cycles that operate on scales of decades and centuries. Research from institutions, including the European Space Agency and NOAA, has shown that the timing of geomagnetic storms matters enormously for their impact. A 2026 study published in AGU Advances found that the Earth's own magnetic pole, which does not align with the geographic pole and rotates around it, changes the exposure of different longitudes and hemispheres to solar wind effects depending on universal time. The storm that hits at 2:44 in the morning local time, as the 1989 event did, hits a sleeping grid. The storm that hits at 2:44 in the afternoon hits a grid under full load with every circuit engaged. The difference in damage potential is not trivial. And there is something deeper still, something that touches the boundary of what science currently measures cleanly and what it is still learning to measure at all. Studies published in peer-reviewed cardiovascular medicine have found that during geomagnetic storms, hospitalizations for heart problems, heart attacks, angina, cardiac arrhythmias, can be up to twice as high as during quiet geomagnetic periods. The mechanism is debated. The correlation is not. The human body runs on electrical signals. The heart runs on electrical signals. The brain runs on electrical signals. And the electromagnetic environment in which those signals operate is not sealed off from the electromagnetic environment of the planet. The sun's reach extends to our bodies in ways that are only beginning to be measured and understood. This is not mysticism, this is biophysics. And it is one more thread in the vast invisible web that connects what happens 150 million kilometers away to what happens inside the bodies of people who have never once thought about the sun's corona. What the data shows right now in the third week of April 2026 is this. Coronal hole 4419 is Earth-facing and actively streaming a high-speed solar wind at 567 kilometers per second, or higher. A co-rotating interaction region arrived ahead of that stream, carrying a compressed magnetic field and elevated particle density. The BIS component swung southward, and Earth's magnetic shield opened. A G2 moderate geomagnetic storm has been registered and continues. Active region 4419 retains the potential for isolated M-class flares. Solar wind speeds of 600 to 700 kilometers per second are possible during the peak of this stream based on recurrent measurements of this hole's prior passes. Forecasters at NOAA's Space Weather Prediction Center say elevated conditions are expected to persist through this weekend. The monitoring is in place, the detection is real. But prediction, the kind that would let a grid operator know whether to curtail load right now or wait 5 more minutes, remains impossible. Scientists are careful to say that, and that careful language carries its own warning. We have 2,000 satellites in orbit today that were not there in 2003 when the Halloween solar storms registered the most powerful explosions ever recorded on the sun. We have electric vehicles whose charging networks depend on GPS timing signals for smart grid integration. We have financial systems whose trading algorithms rely on satellite synchronized timestamps accurate to the microsecond. We have, quietly and rapidly, built a civilization whose highest functioning layers are exquisitely sensitive to the electromagnetic environment of near-Earth space, layers that did not exist in 1989, that barely existed in 2003, and that have been constructed entirely in the window of relatively quiet space weather that followed. The sun has been relatively well-behaved during the years our most fragile infrastructure was built. It has not been well-behaved in the centuries before that. Ice cores and geological records preserve the evidence of solar particle events far larger than the Carrington Event, Events from 775 AD and 993 AD, identified through elevated carbon-14 and beryllium-10 in tree rings and ice cores that were potentially 10 times more energetic than 1859. 10 times those events happened. The evidence is in the ice. The question is not whether an event of that scale can happen again. The question is not even whether, it is when. For now, the storm is G2. The aurora is beautiful over Norway and Canada and the northern United States. The grid is holding. The satellites are adjusting. And 93 million miles away, the sun continues to turn, carrying Coronal hole 4419 past its Earth-facing window and toward the solar limb, where, in approximately 27 days, it will rotate back into view again, because coronal holes do not close quickly. The persistent ones last for several solar rotations. The one that brought darkness to Quebec in 1989 was a recurrent source. This one may be too. And somewhere between now and the next pass, between the G2 storm of today and whatever the biggest component decides to do the next time this hole faces Earth, there is a gap in human knowledge that no instrument yet built can completely fill. The sun's surface is 5,505 degrees Celsius. Its corona, the outer atmosphere where the coronal hole is opened, burns at over 2 million degrees Kelvin, hotter than the surface itself, by a mechanism that physics still cannot fully explain. We have been watching the sun for centuries. We have been measuring it with satellites for decades, and we still cannot say with confidence what it will do next. The system is not dormant. It is awake, and it has always been awake, burning its quiet, steady fusion fire, sending its invisible wind across the void, and we have built everything we depend on inside that wind.